Okay, so we're going to talk about series circuits today. Simplest circuit in the whole world. A series circuit is identified by the fact that it has one path and one path only for the current to follow. If it's got multiple paths, it's no longer a series circuit. Okay, so the first rule of series circuits is the current is constant. It's the most important rule because sometimes when you're looking at different kinds of problems, you want to pull out the series section, and the thing that you can take out of that is that current is constant. Meaning that the current total is the current at any point in the circuit. Okay, current in a series circuit. Total voltage in a series circuit is equal to the sum of the voltage drops. The total voltage in a series circuit is it's additional. And in other words, the voltage drop across resistor 1 plus the voltage drop across resistor 2 plus the voltage drop across resistor 3 is the total voltage drop. The total supplied voltage is dropped across all three resistors. So voltage is additive. ET is E1 plus E2, E3. E is electromotive force or voltage. And ET is, of course, the total voltage. Okay, the resistance in a series circuit is additive also. So series circuits are the most simple because most everything is additive, and then current's constant. And so that means that the resistor of resistor 1 plus the resistance of resistor 2 plus the resistance of resistor 3 is the total circuit resistance. It just adds up. No big deal. Okay. And an example, 6 volt, 20 ohm filament and a 12 volt, 40 ohm filament are connected in series with a 20 ohm limiting resistor using 6 volts and 0.3 amps. Okay, I think that our textbook here, in this case, this is the slideshow from Glencoe McGraw-Hill, and it's not terribly good because of the way they write some of the questions, and this is one of those already where it's not written very well. I wouldn't use this in the beginning just because, but we'll get back to that in a minute. And then the real question of that question was, what's the total resistance? But they didn't make that very clear. Okay. Ohm's law. What is Ohm's law? Remember, it's only one. Ohm's law, there's only one of them, right? He only said one thing. What did he say? Is that what it says in the upper right-hand corner of your 3x5 card? Voltage is equal to current times resistance gives you voltage. Okay, EIR. Okay. Finding total voltage. We can find the voltage drops across each part and just add them up, which is what we're going to do right here. Since the current's constant, R3 is I3, and it is 0.2 of an amp, then the current in all parts of the circuit is 0.2 of an amp. Okay. I'm thinking this may be the end of this slideshow from the manufacturer, which is just fine. Write the formula of finding IT, ET, and RT in series circuits. You don't have to write the formulas for those. You have them on your 3x5 card. In the upper right-hand corner, you have EIR. PIE in the upper left-hand corner is the power. Power, I, current, R, resistance, right? And then EIR. And then we're going to talk about deriving two other formulas. I think we're going to do that today, if we have time, and I think we have time, pretty sure. I don't want to get into this problem either. Unbalanced AC load. We don't even want to talk about an unbalanced AC load, I don't think, just now. Transposition, mathematical idea we do need to talk about. Okay, in this problem, they're talking about adding a resistor to a circuit, but you're not up to this point, I don't think. So don't worry about that. This is where they have a certain load, and they're going to add resistance, so they change the voltage that's going across the other parts. But we're not at that point just yet. Now this is an example. I think I stuck this in, and this is more like what we do. Now you'll notice that we have a couple things. We have a voltage on resistor 1. We have a resistance on voltage 1. And from that, we can find out what? The current, right? So we can find the current at every one of these points. Over here, we have R2 is 45 ohms and R3 is 20 ohms. So if we find the current, we can find everything, right? So if we have E and R, look at your 3x5 card and tell me how we would deal to find the current. E, what do we do with E and R? Divide what by what? The voltage by the resistance, right? So we're going to divide E by R. So we divide 8.5 by 35, we get a very small number. What is it? Say again? Thank you. So we have, and I will always put it as E, I, P, I, P, I, E. Sorry, I got that all. No, I'm thinking of something else. Sorry. Okay. So we're going to start writing PEIR next to every part of a circuit. We're going to put it over here. PEIR. PEIR here. PEIR and PEIR. And the magic part of that, writing it that way, is that if you write it that way, if you're going up, you multiply. If you're going down, you divide. Okay? Piece of cake. So here we have E and R, and we know we're going to divide because we're kind of going down. So we had what, 2.4? Was that right? 0.24? Oh, 0.24, thank you. Well, that was good. Now, as long as we're on this, we would never say 0.24 ohms. We'd move the decimal place to the 3 places to the right, and we would say we have 240 milliohms. And anytime you have a quiz question, put it in proper engineering notation. It's okay to write, as you're going through this stuff here in the middle steps, it's okay to write 0.24. That's probably easier sometimes. But when you move that answer to a line on an answer sheet, make sure you put it in proper engineering notation. Okay? So 0.24 becomes 240 milliamps. Small m, big A. Okay. So that now we know that this R2 is 45 ohms, right? And we know that the current is 0.24, right? Everybody with that? So we're going to multiply up to get the voltage. 45 times 2.24 is what? All right, so we're going to go to the next one. We know we have 20 ohms here. And we know that we have 0.24 amps. And again, we're going to multiply up. And we have what? Is that 48 volts or 4.8? 4.8 volts. Okay. Okay. So now we have all three resistors, right? Okay, now what we're going to do here is we're going to assume that we have 0.24 amps here, 0.24. And if that's true, we can look at our resistors and just add them up because resistance is additive in series, right? So 20, 45, that's 65, plus R1 is 35, so that's 100 ohms exactly, right? Everybody agree with that? Somebody check it. Use that calculator. Okay, so we have 100 ohms. Now, if we multiply this up, what do we get? 24 volts. Now, here's our pure functional magic. We're going to add up our voltage drops because that's just add up to our voltage supplied, right? So here's our pure functional magic check. We're going to add up 4.8, 10.8, and 8.4, and what do we get? No. Pure functional magic, I tell you, it added up to the same thing we thought we would have a supply. So that's called a cross check, or pure functional magic is still working. Okay? So let's try another one. Oh, doesn't like me holding that. Okay, so now we have another problem, except now we have 1, 2, 3, 4, 5 resistors. But we're given a current this time, and we have resistance, voltage, voltage, resistance, and resistance. Oh no! Whatever shall we do? That's too confusing. I'll never figure this out. But we have current, so we have two things in every part of the circuit, right? We have 250 milliamps. Okay, and we have 200.250 amps. And we have a voltage of 5 volts. But we also have 0.250 amps. Right? So we have two things there. We have two things here. We have voltage here. And we have a voltage of 12.5. We have a current of 0.25 amps. Down here we have a resistance. How many ohms is 5K ohms? 5,000. They put it in proper engineering notation. Okay, I like that. And we still have a current of 0.250 amps, or 250 milliamps. Then over here on this last one, we have 15K, which is 15,000 ohms. Now, you'll notice every place except our totals, we have two things, right? So let's just start doing a little math here. 10,000 times 0.25 is what? Now, I want to show you a thing about engineering notation. Now, this is kind of a bad time to do this, but I don't think there's going to be a good time. So I want you to see this, and I'll erase this in just a second, but 10,000 is 10 times 10 to the third power, right? Everybody agree with that? Okay, 10 times 10 to the third. And we're going to multiply that times this right here, right? Now, what is 0.250? That's 250 times 10 to the minus third, right? Everybody agree with that? We move the decimal place 3 places to the right. We have to multiply times 10 to the minus third. So it's 250 times 10 to the minus third. Now, what happens if we have 10 to the minus third times 10 to the third. 10 to the 0 is what? 10 to the 0 is 1. Okay? So we simplify this thing out with engineering notation to say it's 10 times 250. You know what? I think I can figure this one out. I bet it's 2,500. What do you think? Everybody agree with that? That, or you can do it with a calculator. 10 times 10 to the third, or 10,000 times 0.250. Do it with a calculator. Make sure it's the same thing. We've got to check our pure functional magic. Does this come out to 2,500? Amazing, I tell you. Pure functional magic. Okay, so now you see one of the shortcuts that using proper engineering notation will give you in electrical work all the time. Okay? It'll provide that for you often. Okay, so let's go back to our second one. We have 5 volts times 0.250. Just do that with a calculator. What do we get? Very small voltage, right? 5 times 0.250. Oh, we're not multiplying. We don't. That would give us a very small amount of power. We're going to divide 5 by 0.25. We're going to divide because we're going down, right? 5 divided by 0.25 is what? 20? I'd have sworn it was going to be 25. Okay. 0.25. Okay. My brain has a dysfunction, that's all I can tell you. Okay, so now let's go to the next one, and we have 12.5 volts, and we still have the same current, so let's divide 12.5 by 0.25. Three different answers. 50? 12.5 divided by 0.25. I think you left out the point. 50? Got 3 votes for 50. 50 ohms. Okay. Okay. So now on the next one, on R4, we have 5,000 ohms of resistance. We have a current of 0.25, so we're going to multiply up. 5,000. Now again, here we could write this as 5 times 10 to the third, right? Times 250 times 10 to the minus third. Notice that those are going to drop out. 5 times 250, I've heard that's 750. 1250, sorry. I guess I've heard wrong. I was thinking of 3 times 250, sorry. With my writing, it's hard to tell sometimes. Okay, so now we're going to go to 1,500 times 250, and now we can replace this with just 15 instead of 5, right? 15 times 250. 10 times 250 would be 2,500 or 25,000. 10, 1, 2, 25,000? No? Okay, what's 15 times 2,500 times 250? 3,750? Okay, I can go with that. But that just doesn't look right. Oh, it's 2,500 plus half of that. Okay, got it, got it. Okay, 3,750, that's right. What am I doing? By the way, I want you to notice what I was just doing mentally. What was I just doing? Ballparking? I may be wrong sometimes, but when I do a finger calculation that's way off, if you've done like a mental ballpark of that answer ought to be somewhere around, if you've done that ahead of time, when you come out with an answer that's way off, a little red flag will go up and go, well, let's go back and check that. Maybe I punched in the wrong keys. Maybe I left out a decimal. Maybe I put the decimal in the wrong place. Okay? And you want to do that. You want to start getting in the habit of, that probably ought to be in the neighborhood of, it'll avoid a few mistakes here and there. Okay, so now we have everything, right? Except power, because we haven't started talking about power yet. That's okay. We can just multiply E times I and get power, right? That's not a big deal. So let's look at this over here. Let's add our resistances up. 1,500 plus 5,000 That's 20,000, right? Plus 50, 20, and 10,000. Okay. 20, 30, 30,000 plus 50. Is that 30,050? Anybody agree with that? Add those up for me. 30,070. Oh, 50 and 20. Sorry. 50, I thought it was 50 and 20 and 30. Okay, so 30,070, right? Anybody agree with that? So P, E, I, R, and we have 30,070. Is that correct? Okay, and we still have 2,500 microamps. Oh, shoot. I've been doing it at milliamps. Microamps is 0.000, 0.00025. So everything's off by a factor of 10. Okay, so we're just going to, what we're going to do is we're going to finish solving this with this as an M instead of an A. I mean, instead of a micro. Okay, so someone should have caught me on that and said, hey, that's not milli, that's micro. That's okay, though. My fault. So anyway, we're going to assume it's milliamps because I've done all this calculated with milliamps. So 30,070 times 0.25 would give us what? 30,070 times 0.25. $750, 750. Okay, repeat that number again. 751 7.5. Anybody agree with that? Everybody agree with that? No? Okay, well let's do the pure functional magic check first. Clear your calculators, and now we're going to do the hard part. We're going to do some addition. Okay? 3750 plus 1250. You know what? We didn't work one out. Yeah, we did. 12.5. 5. And 2,500. Now hit enter. Amazing! Pure functional magic at work. The gentleman has the number correct. Yay! 5-1. No, 7517.5. All right. Good job. Now, oh, that's the end of that. Okay, so now we're not going to stop recording. We're not going to stop doing this. Let me pause for a second, that way I change back. Okay, one of the problems we're going to have sooner or later is we're going to be looking at a situation where we have a solid voltage supply of, say, 12 volts, and we have two resistances or two loads, and we've got a variable resistor. In other words, if I've got two resistors and I can change the resistance of the third set, what do I want to set it at if I want to have the current at a certain place or something like that? So let's assume that we want to have we want to have 1 amp flow through this whole circuit. Okay? So we know that we need a total of 12 ohms, right? Because it's a one-to-one thing here. Make it nice and really simple. So we can see that if we want to have a voltage total of 12 volts, and we've got 5 volts plus 2 volts plus E3 is equal to our 12-volt supply. So we're going to subtract these two from both sides. That's our 7 volts, so 12 minus 7 volts is equal to E3, right? So we know that we want to have a voltage drop across here of 5 volts, right? 12 minus 7 is 5 still? Okay. And if that's true, then we'll have 1 amp current flow all the way around this thing. Now that's an extreme simplification to make it really, really easy to look at. But this thing of, you're going to do problems with this chapter where you're going to have to find out, you have to decide on what this other resistance is that you're going to add in to make the circuit balance out. Okay? And that's series circuits. That's pretty simple stuff. Okay?